Okay, good morning from my side. I would like to recap first what we did last time. So it's here on the board. I wanted to stress key features of stochastic processes that we discussed, and I have written it on the board for a set of random variables that are discrete, so meaning they take numbers, integer numbers. Then we learned two quite important concepts that are really fundamental to the theory of stochastic processes. The one is that we have a master equation. This master equation is the underlying equation for the time evolution of probabilities for discrete random variables. And that's why it's called master equation. It's really the foundation of how you describe a stochastic process. If you want to solve it, then there's various methods, and you saw some of them, generating functions, looking at the moments, a lot of different things you can do, and we will discuss more of the methods of solving master equations as we go along in the lecture. One key way of solving stochastic processes is the stochastic simulation algorithm or Gillespie algorithm. It's an exact representation of the corresponding master equation. And what you get from simulating that is you get a set of stochastic trajectories. And as you sample many of those stochastic trajectories, you get a histogram. And as you continue to sample, this histogram is supposed to converge towards the probability density that's described by the corresponding master equation. And that's what it means that the Gillespie algorithm is an exact representation of the corresponding stochastic process. Okay? Now, what we did also is to discuss two paradigmatic examples of elementary stochastic processes. One is the random walk, and the other one is the Gillespie algorithm. The Poisson process. And for the Poisson process, I explained to you the essence of the Gillespie algorithm. Now, I want to discuss with you, what do you remember for the random walk? What are the hallmarks of a random walk? It's up to you. Yeah?
I think we had discrete time steps and we hopped.
Yeah?
Basically, master equations doesn't seem to be applicable here, but probably this.
We had a master equation for that. We did. And I just wanted to know from you, what's the outcome? What do we know about the mean? What do we know about the variance? What's typical for a random walk? And what is the ultimate limit in the long time limit for the probability distribution function of a stochastic process? Please go ahead.
Yeah, so the mean increases linear in time with some velocity, average velocity.
Yeah.
And the variance also increases linear with time, meaning the standard deviation is squared in time, according to some diffusion coefficient d.
Yeah.
And now depending what steps we took, I think we took binary coin flip steps.
Yeah.
But however, you could also take Gaussian steps or whatever. In the long time limit, we converge to a Gaussian distribution.
That's exactly the point. In the long time limit, independent of really how you do it in detail, if there are no strong correlations between the steps, the central limit theorem always tells us that P of n and t is converging towards a Gaussian distribution, being, we know, with a mean or without a mean, depending on how you define it. And that's really the universal limit of a random walk. And it's connected basically always to a very important theorem that you all know, which is the central limit theorem. Now, for the Poisson process, what's the corresponding statement we made about the mean and the variance? So let's say Poisson process is hopping forward with a certain rate nu from one side to the other. Right, what's the mean? What's the variance? Don't be shy. Go ahead.
Mu and the mean
Yeah, that's the point. So I repeat here, both the mean and the variance go like nu times t, where nu is the hopping rate for a Poisson process. And that's quite a hallmark of that. So it's really that they are identical, and that means the ratio of variance to mean is 1. Okay? All right, so that's the recap of last time. What we will do today is two things. In the first 45 minutes, we will do population dynamics. And I explain to you again how master equations work and how you apply the Gillespie algorithm in a more elaborate context. So you see really how it works out when things are getting more complicated. And then as a second, in the second half, I will talk about the formal mathematical structure for stochastic processes. And what we will focus on, I guess in all of my lecture, it's what's called Markov processes. And you will see what this means, what I mean by Markov process. Okay, so let's start. What we did first last time, and I recap a few steps for that. We looked, so it's about population dynamics today. And the simplest case we are going to look at is the linear death process. And for that linear death process, what we say is that we have individuals A, and they decay at a certain rate lambda, and lambda is the per capita, so per individual death rate. Okay. Famous examples of such a process is, of course, the radioactive decay, where particles decay at a certain rate. Now, there's various levels of description. One I didn't mention last time. Let's call this a deterministic or a mean field description. And what I mean by that is I ignore now for a moment that the process is actually stochastic, and I try to write down an equation for the typical number of particles that you have in the system as a function of time. And it will turn out, if you do the analysis, this equation will apply on average. So let's talk about a variable n of t, and let's ask, what should I write for the time evolution of this typical number of particles as a function of time? Well, that's kind of obvious. This means it decays with a rate lambda. The rate lambda is a per capita rate. So you get the classic equation of radioactive decay, which is minus lambda n of t. And of course, you all know how to solve that. The solution for that is the initial particle number that you have in the system, and then things decay exponentially. But that can't be right in the limit of infinite time, because it means that the particle numbers that you write down here, they will approach numbers that are below 1. They're real numbers, and that can't be. You have either 2, 1, or 0 particles. So there's something wrong about this description, especially in the limit of long times. In the limit of long times, we know that a certain number of radioactive particles at some point all have decayed. And that doesn't happen here for a deterministic description. So what we do instead, and we went through that last time, is a stochastic description. So a description how it actually works in terms of random variables, and then the object of study is no longer a single particle number, but it's actually the distribution function, the probability distribution function for a given number of particles at time t. And what we wrote is gain minus loss. So this was, I'm gaining if I do have n plus 1 particles at time t, and I'm gaining at a rate lambda times the number of particles, and I'm losing when I'm in state n with a rate lambda times n times p of n and t. Okay, and that master equation you can solve. There's a tutorial in my lecture notes where you guide it through how you solve this with generating functions. There's a simpler way, though, to argue. Namely, you can put yourself in the position that you consider a single individual and you ask yourself, for that considered single individual, what's the probability of that individual to actually die or survive in a time t? Well, the death probability, so p of t, is e to the minus lambda t, and the complement of that, q of t, is 1 minus p of t, 1 minus e to the minus lambda t. And once you have that, once you know what an individual does, you can write down probability density for all n particles, but just looking at this as a classical binomial problem, as we have done that also in the previous lecture. So you would write down that the probability of my system to have n particles at time t, this is the number of possible options to go from n naught to n. This is a binomial factor. And then you multiply this by p of t to the n and by q of t to the power n naught minus n. Okay. So that's what you have. And yet you can also show using other methods. This is basically guessing what the solution is. And for that, you also know what the corresponding mean and variance is, because that's a binomial distribution. And for a binomial distribution, we know that the mean is n times p, so n naught times e to the minus lambda t. And you might recognize this is exactly the result that we found from the mean field or deterministic solution. It's the average number of particles that obeys such a deterministic equation. And you can also show, just from the binomial, that this is n naught p times q, so e to the minus lambda t, 1 minus e to the minus lambda t. All right. Now, this is an analytic description of the stochastic process. Let's turn now to a stochastic description in terms of numerics. So let's turn to the Gillespie algorithm for our linear depth process. And as I taught you last lecture, the basic quantity you need is the survival probability, because the survival probability will give you the typical time for the next event to happen. So let's say I start at some time t naught with an initial state given by n of t naught, so a given fixed number of particles that I have in my system. And then I'm asking, what is survival probability of that number that we have at time t naught at some time t plus dt later. And as we argued last time, you can dissect this into the probability of survival from t naught to t. And then in the small time increment, I have the conditional probability, given the number of particles, what is the chance of these particles not decaying? Well, and that's 1 minus n of t lambda times dt. So it's the number of particles at time t times the rate that they decay times dt. That's the probability of one of the individuals to die. And I want it to be the probability of not to die to survive. So that's 1 minus that. Now here you have n of t. And I can replace that. I can replace this by n of t0 because I'm starting from a population of n of t0. And I want it up to the time when nothing has happened yet. So I can replace this by n of t0. Okay, that's my survival probability. I can write down a corresponding differential equation. I don't have to repeat that. You know how to do this. And then once you write down the differential equation, you can solve it in the same way as we have done it last week. And what you get is e to the minus n of t0 times lambda times t minus t0. This gives, as you take the derivative, the waiting time distribution. And from the waiting time distribution, you can calculate the random variable for the waiting time. And that now is tau equal to minus 1 over n of t0 times lambda times the log of xi, where xi is a uniform random variable in the interval between 0 and 1. So all that has really changed here is that I have now in the numerator not the Gillespie time for a Poisson process, but I have the corresponding time, rate for the process in our case here, which is the number of particles times the rate. So what's different from before is now you have a dependence of the rate on the configuration of the population at time t0. In the Poisson process, there was no dependence on that. It was just the rate. Okay, that's the setup. And now I can simulate the stochastic process using the Gillespie algorithm in the same setup as we had this last week. So let me show you the corresponding simulation. All right, so here you see the simulation. On the right-hand side, in the solid black line, you see the result from deterministic time evolution, so exponential decay. This captures the mean quite okay. The colored lines that you see are stochastic trajectories, and you see they decay following the mean, but also deviating from the mean since there's some variance. And most importantly, there is some time points here, here, and there where the number of particles actually goes to 0. Okay? So there is another stochastic problem here that we need to study and didn't do yet. Namely, what is the extinction time for such a population, and what is the characteristic of that extinction time distribution? What's the mean? What's the variance, etc.? All right, if you look on the left you see histograms that are obtained from stochastic simulations like shown on the right. So I just sample over many different trajectories. and I put them here into a histogram, and the histogram shows the probability, or the proxy of the probability for particle number n at time t. This is here at a late time, this is at an earlier time, and this is at an even earlier time. So you see this distribution that you have initially moves towards the boundary, where you have a state that's absorbing, because once things are dead, they will not be recreated in the process that I study. And as you see, the mean shifts according to this law, and the variance, if you check it, really follows the variance that I wrote down here. So the variance also goes to 0 in that particular case as e to the minus lambda t. Okay, so that's what we have for the linear depth process. Are there questions? If not, then I would like to move on and study a more elaborate process for a population dynamics problem. And this more elaborate process is called the Lotka-Volterra process. Let me define it. So the second is the Lotka-Volterra model or process. And it contains two types of particles that I call A and B. And A I consider a predator, and B being the corresponding prey. And we want to know how this interaction between predators and prey, where both of them are born and die, how that leads to the time evolution of the whole population of a certain number of predators and number of prey. So let's write down the processes. So I want that there is a certain death rate for the predator, and I'll give it the same name as before. The death rate per capita is lambda. So this is a death process. And I also want that my prey is born at a certain rate. So one individual gives rise to an offspring, and that's why B goes to 2B. And I'll give this also a rate, and that I call mu. And as before, lambda is per capita death rate, mu is a per capita birth rate. So what else should I have in the system? I also want the system to have some predation. Okay, so you have here A being a predator and B being a prey. Predator eats the prey. So I want to replace this here by A eating B. And then in a very coarse-grained fashion, I kind of say, as soon as A eats a B, it reproduces itself. Okay, that's a coarse-grained description. That's not as it happens really in detail. But on a larger time scale, you can think of this as the way of the predators to survive and reproduce. And that's I call predation. Now, there's also another process when you have lots of particles in your system, meaning lots of prey in your system. At some point, they will reach a certain carrying capacity where the environment in which they live is no longer able to sustain their growth, and I also need to account for that. And in the model, this is accounted in the following way. So there is, when there's too many bees, they can't sustain themselves as a population. So there is an effective death rate because of the competition for resources. So B plus B goes to B. And let me give those rates here a name. I call this gamma with a subscript P for a rate for predation. And this here I call gamma C for a rate for the competition. That's the model. Okay? We don't debate the model. This is not a super realistic model for population dynamic, but it's a good start to learn about what's happened, and it has, famous bunch of people that came up with that model quite some time ago. So how would you describe that now? Well, let us first write down here not the per capita rates, but given a certain configuration of my population, meaning a number of predators and prey, the effective rates of birth, death, etc. So here I have my first rate at a given time t naught, which is the effective death rate. And then this is given by the number of A particles at time 0, and that's what the symbol here means, times the per capita rate. These quantities, you can also, they're also called propensities, but let's call them for now effective rates of birth and death in the population. Well, what do I need to write down for this second effective rate of birth? I just have now the population size of B individuals, and each of those B individuals, NB individuals at time t equal to 0, gives rise to an offspring, so the effective rate is the number of individuals times the corresponding per capita rate. What about this here? So I have alpha 3 T0. It also depends on the number of individuals, but now in order for that process to happen, an individual of type A has to meet an individual of type B. And that probability is proportional to the corresponding abundance of individuals A and B. So I'll write down here NA0 times NB0 times the per capita rate, gamma p. Now for the fourth one, I have to ask myself, given this well-mixed population, right, there's no explicit space here in the population, what's the likelihood of picking an A and another A? So the likelihood of picking an A is proportional to NA0, but then I have picked one. That means the likelihood of picking the next one is NA0 minus 1. Okay. So we have NA0 times NA0 minus 1 times gamma C being the rate of composition. Yeah?
You mean that for B, right?
Oh, sorry. I mean this for B. Thanks. So I hope that's clear. This is how you set it up. Of course, you can debate a bit of what you should write here, gamma C. Should you write gamma C or gamma C over 2? Because, there's different ways of picking the two individuals. But in the end, there's a choice here because it's a rate. And then in the end, it depends on how you actually measure the rate and define it. So let's define it this way. That's our rate of competition. Okay, now let's ask ourselves not how to write down a master equation. You could. It's not a big deal. It's just very cumbersome because it has a lot of terms. Let's ask ourselves how we set up a Gillespie algorithm. So let's start from an initial state, and let's call this C of T0. And here in our present situation, this initial state is the number of individuals A and B. Now, given that is initial state, what can happen? Well, what can happen is really already listed on the upper part of the board. Any of these four processes can happen. There can be a birth process, a death process, a competition process, or a predation process. And each of them has a certain rate, and this rate we wrote down. So we have a rate alpha 1 of T0 of death. We have a rate alpha 2 of T0 of birth, etc. Those are the four different processes that can happen. And this is A going to 0. This here is B going to B plus B. This here is predation, A plus B going into A plus A. And this is competition for resources, so B plus B going to B. Now, how would we do a Gillespie algorithm for this type of process? That's our question. Well, you ask yourself the following question, not what happens specifically. You ask yourself, when does something happen? Anything of those processes, either birth, death, predation, or competition. Okay, that's the first question you ask. And this first question you can formalize in the same way as we did this before. So you say you start from some initial configuration at time t0, and then you ask, how long is the whole configuration surviving up to time t plus delta t? Again, you can dissect that into the survival probability up to time t. And then you need to multiply that with the probability of nothing happening during time dt. No birth process, no death process, no predation, no competition process. And that's 1 minus the sum of the probabilities of all these independent processes that can happen. So we have 1 minus alpha 1 t0 dt minus alpha 2 t0 dt, etc. And I'll give this whole thing here a name. This is then the total, the overall propensity. So I call this 1 minus alpha of t0 dt. So alpha is just the sum over all the different rates. Again, you can write a differential equation. You can solve the differential equation just as for the linear death process. There's nothing that's more complicated in the analysis than for the linear death process, because in the end, it's just asking the very same question. How long does it take for a certain state to survive, given that I know the total probability of something to happen, which is the alpha? So this is e to the minus alpha at t0, t minus t0. And that means now my random variable that I have to choose when I want to create a Gillespie simulation is I take the log of a random variable uniform in 0 and 1, and I multiply by minus 1 over the overall rate of things to happen. Okay. So that is the typical time. No, that's not the typical time. It's the time to the next event. That means any event out of the list that I gave. Okay? Once you know that something happens, you still have to evaluate what happens. Okay? And that's the next step. So next you specify what event happens. So we give this a probability mu. Mu is now the particular event, 1, 2, 3, 4, that I'm looking at. So what is that? Not hard. It's the rate of that event divided by the overall rate. It's the relative probability of things to happen. So this is alpha mu of T0 divided by alpha of T0. And that's really it, right? You calculate the time point when something happens, and then you calculate which of the events that are in your list of possible events happens and what's the corresponding probability. Yeah?
I mean, it's obviously a natural choice.
Yeah.
I think that's possible. Is there any formal way to think of this or get this result by a computation or proof or something? I mean,
it's just that,
yeah, one thing, of course,
yeah.
But why exactly?
It's by the definition of what rates are. Rates are probabilities per unit time. So I could write this as alpha mu T0 times dt. Then you have the probability, and you divide it by the total probability of something to happen. So I'm just using the definition of what a conditional probability actually is. Okay. Not more than that. Yeah. So it's just the definition of conditional probability, not more. It's as formal as it gets. All right, so now let's go to the slides again. Okay, and here I just wrote in words the program, basically, that you have. So you start with an initial configuration. In our case, it's 2 numbers because they completely specify the population. It's the abundances of predators and prey. Then you choose a first random variable, psi, between uniformly in 0 and 1. And from that distribution, you calculate the time, t minus t0, so the time spent between having this initial configuration and having a new configuration. And that's minus the log of psi divided by alpha, as I just showed you. Then you want to calculate the relative probabilities for the individual processes that can happen. And for that, we need to calculate p. And again, you have to now choose a random variable, which you give another name, call it zeta. And zeta we also take randomly between 0 and 1. Now, instead of reading to you the complicated equation that's written here, let's just look at this graph, because that's easier to see. So you have these relative probabilities P1, P2, P3, and P4. And of course, they have to sum up to 1 because those are mutually exclusive events, and they completely specify what's happening. Now, the random number you choose is between 0 and 1. And wherever this random number hits, so in the interval P1, P2, P3, or P4, that's the process you take because that's the likelihood of the corresponding process that we study. Well, then you're done. So 2 random numbers, then you specify the complete process, and you update time, and you update the configuration, and the whole thing starts anew. Good. That's the process. Are there questions before I continue? Now, let us ask how I would write down the equation in the same way as I did it here. So a mean field equation. So equation directly for the average, not an equation for the random variable. How would I do that? Okay, I'll show you. These are the rate equations, and I'll guide you through so you'll understand what's here on the board. So the first one is the average number or typical number of predators in the system. And the right-hand side gives the rate equation for this process. So what's the first term? Minus lambda a. Well, that's just the linear death process that we also had for the linear death process before. The second term is gamma pba. That's just a continuum version of the term that's predation. So if a B meets an A, you have a process that corresponds to predation, and that increases the number of predators correspondingly. So you have here a loss process due to death of predators, and here a gain process because of the predation of the prey. Now the second equation is very similar. The first term is the birth rate times the typical number of B individuals. And the other two terms, they correspond to both predation and prey. If you want to have a predation event, then you lose here. This is a minus, and the loss is proportional to the concentration of A and B times the rate. And similarly for competition, the rate is proportional to gamma c times the square of the density of particles B and B. And that's what you would write down if you were to be a chemist and write down chemical reactions. Those are just the mass action laws you write down for a chemical reaction, also known as rate equations. Good, they're much simpler than the corresponding stochastic equations. So here is the specification of the stochastic processes, and they involve all these different rates, and as you write the corresponding master equation, try it for your own. It's a lengthy object that you need to write down. All right. Now let us analyze these rate equations for a bit, meaning just look at the properties of those rate equations from the perspective of analyzing ordinary differential equations. And I wrote down here a simpler special case where I say that there is no competition for resources in the system, so gamma c is actually 0. And then it turns out, and that's not so obvious to see, that this set of equations in the limit of gamma c has a conservation law. It has a quantity E that's given by the right-hand side. And as you would take the time derivative of this quantity E, it would not change in time. So it's like an energy that you have in a classical mechanical system. It's a constant of motion. So now you have a constant of motion. What would you guess the trajectory should look like for A and B? In a space where you plot on one side, on one axis, B, and on the other axis, A. So like in classical mechanics where you have position and momentum. Yeah?
The circle of this.
Yeah, something that's closed. Why?
Because we have to go back to original point at some point.
Yeah, because conservation law, so you can dissect the phase space into trajectories that are 4 given, let's call them energies here. They're not energies, but values of E. So there needs to be some closed trajectories going around a certain way, and each of those trajectories is characterized by an individual value of E. All right, and indeed, that's what you get. These are typical trajectories that we have for different parameter sets. So on the left-hand side, you see it for the case I just mentioned, so for gamma c equal to 0. And then there is a stationary point in the middle where nothing changes. But surrounding that stationary points are all these closed orbits, and they describe oscillations, right? Oscillations of the population. A goes to B, goes to A, and there's a mutual balance between things growing and shrinking in the predator and prey population. Each of those trajectories gives rise to an oscillation. On the right-hand side, I gave you the same phase portrait, that's the name of such a representation, where gamma c is finite. So where you have some kind of competition between the individuals, and then it turns out there's still this stationary point or fixed point, but that fixed point now is actually a stable fixed point, meaning that all trajectories that I have ultimately will spiral in and converge towards that stationary value. So there's still some kind of oscillation in the population, but in the end, the system goes to a stationary steady state of a time uniform concentration. Okay, here you see what we get in a corresponding simulation of the stochastic dynamics. So that's using now the Gillespie algorithm as I wrote it down to simulate the same thing, now spaced out in time. So meaning I start with some initial population here, and then I have 2 different trajectories, and those 2 different trajectories, they show some kind of time evolution. What do we see? Well, we see this gamma c equal to 0, so it's supposed to be on average the same object as the mean field equation that I showed you, and indeed it shows oscillations. They're not, of course, as nice as the actual oscillations, because the actual oscillations would be really nicely uniform. Here you have a lot of randomness in the oscillations as you have it, with the amplitude going sometimes a little higher, sometimes a little lower, and the trajectories not being smooth, but more like random as you know it from random walks or from Poisson processes. Here, this is the corresponding stochastic simulation compared to the deterministic simulation for certain time windows. Let's look again on the left-hand side. So the left-hand side is for gamma c equal to 0. There's no damping. You have these closed oscillation cycles, these predator-prey oscillation cycles. And if you look at the stochastic simulation, it's similar, but it's of course not identical. So some features of the process are similar to the one that you find from deterministic simulation, but others are quite different. This becomes even more pronounced, this difference between the stochastic simulation and the mean, when you look at a case where gamma c is finite. There you do have, for a deterministic system, that the oscillation ceases completely, right, as you see. You have these oscillations, they become weaker and weaker, and in the long run, steady state. What do you see from the stochastic simulation? It doesn't stop, right? So it's continues oscillating. Why does it continue oscillating? What intuition should you have? Try it.
I don't know really, but maybe it's because our population size is again a discrete number, so
Yeah.
we cannot have a exponential fade out again. And as soon as we only have one Frey object, it's like growing again. Maybe something like that.
That could be a reason, but still that would mean you just have little fluctuations because of not having a real number, but an integer number. And if you would take population size to really, really large values, that distinction between real and integers wouldn't really matter. So it's not the reason. Let me show you the intuition that I want to convey. Let's go back. To this here. And let's look at this one here. Okay. So that's a deterministic trajectory. It winds into the fixed point. Now, stochastic process means that here, even there, when you have a steady state in deterministic dynamics, there are stochastic processes. Okay? And you can think of them as random walks in phase space. So on top of the deterministic process, there's a random process superimposed. So as you land here on this point, there's going to be some random kick that takes you nearby or far or further away, because it just happens to be that there are a lot of, say, events that increase the number of A, or a lot of events that increase the number of B, or anything of that. So basically, and that's how you should think of this, you're pushed by the stochastic process out of this fixed point, and then you can't go back directly. You have to, on average, go on these cycles and cycle back in to the deterministic state. And that's what you basically see when we now look at these trajectories. Okay. So here, the system has this tendency of focusing you at the steady state, but then there are some deviations. They're kicked out of this steady state, but there's always this tendency of bringing you back and bringing you back, and there's this balance between the random process that tries to kick you out from the center and the deterministic process that tries to convert you back to the steady state. Okay? Let's stop here and take some questions.
So, if the random processes are so powerful that it can deviate you from the center, so it can make your position far from the center.
Yes.
So, shouldn't they be the same for every types? For example, for the previous gamma, C equals to 0, and gamma C equals to a little quantity. So, for both of them, because at each place, the random processes push us away from where we are, we should see the same picture.
So let's look at this one. Very good question. So if you here, on one of those trajectories, that's gamma C equals 0, there's nothing making you drift in or out. So on that landscape, as you go perpendicular to these lines, there's no force, in quotation marks, that pushes you to the fixed point or away from it. And that means in this space perpendicular to these contour lines, you perform a random walk. So you're right. There is a random walk on top of this deterministic process, and that's what you see in the stochastic simulations. There's also something that happens I did not show you because it's rare. Namely, the stochastic process can also kick you at the boundary of that. So, and as you kicked at the boundary, something weird can happen. Right? So here, if you kicked at the boundary to a system where you have only B's, then the system has no competitor anymore. It just explodes. And here, if you would have a system where you just have A's and B is 0, then you push towards extinction. Okay? So you have this on top of these random events that modify the deterministic trajectories. They are random events that are really strong and rare because they lead to an extinction of the whole population. Yeah?
What if you have dissipation in this system, which drives the state point towards the stationary?
Yeah, so dissipation here is encoded, if you think of this in terms of classical mechanics, because that metaphor is what you have in mind, I guess. This is a system that has no dissipation in that metaphoric sense because there's no competition. And then you have this conservation law where you have this conserved quantity E that describes the dynamics. The gamma C plays the role of a dissipation effect because it makes the system deviate from the conservation law. There's no conservation law anymore, such that the system then dissipates, quote, quote, into the steady state that you have there.
So we have Lagrangian or Hamiltonian for...
That's the wrong language here. That's the wrong language. So this is not a classical system in the sense that you have classical mechanics and you use a description in terms of momenta and position, and you work in terms of a Hamiltonian and things like that. That's not the description level that we have here. Hamiltonian mechanics is a ODE type of system that you can analyze in a similar type of way. Here, I don't even argue in this kind of framework. This is a framework where I just talk about population of individuals and not about some underlying classical mechanics framework. Yeah?
Just a question again about those runaway states you have at the very left. In the stochastic picture, you would have a... I'm sorry, I don't know.
Go ahead.
What my voice is doing. So if you go, maybe the next slide. Again, like the slide we just saw where those two plots were. You have a finite probability of going into one of those runaway states, right?
Yeah.
In the stochastic picture.
Yeah.
But in the deterministic picture, you basically have boundary where you have to do this is measure 0, so you have kind of a 0 probability of reaching it. It's kind of maybe between discrete and continuous in this sense.
Yeah, exactly. In this good observation, it's in the same way as the linear death process. The linear death process in deterministic description never goes to 0, only at infinite times. And if you make it discrete, you have a finite time where things die. Same here. If you make it discrete, at finite times you go to the boundary. If you don't have a discrete description but a continuous description, you can't reach the boundary in a finite time, unless you make the flow such that it does. But in the case we see here, it doesn't happen. Good, then let's have a break, 15 minutes, and reconvene at 11:30.